This video will go over the basic control and dynamic systems of a servo motor. The servo motor used in this video is an HS 475 HP Deluxe made by Hi-Tech. I'll now take apart the servo motor to get a better understanding of what it looks like on the inside. The basics of a servo motor is made up of a microcontroller, a DC motor, and a potentiometer. The inside of the servo motor looks like this, and we can see there's a microcontroller, and on the other end we have the gearing ratios that connect the DC motor to the potentiometer as well as our control surface. With the gears removed, we can see the DC motor, which is the middle shaft, and the potentiometer, which is the right gold shaft. This is a schematic of our control systems for our servo motor. Our input is the receiver signal, which is our desired position, which is specified by the user by the rotation of a steering wheel. This is sent into the microcontroller, which consists of a PID controller and a transfer function, which is then sent to the servo motor and results in a rotational motion. We have a negative feedback loop, which is a potentiometer that displays the actual position of the controlled surface. This value is compared to our desired position, which is inputted by the user and is then sent to the microcontroller, which accounts for this error and moves the control surface as needed. Now let's look at a physical example in which the potentiometer is disconnected from the DC motor. The potentiometer will continuously send the signal that is at home despite not actually being at home due to this disconnect. This will cause the motor to constantly rotate as it does not believe it has reached the desired position inputted by the user, as the potentiometer is not updating and is still saying it is at home. Now let's look at it the reverse way. With the user not rotating the wheel indicating that it is at the rest position, let's force the pot. See, as we force the pot, the motor rotates to compensate for this. However, because the pot is not connected to the motor, it is not updated, resulting in the motor indefinitely rotating as the pot is solely controlled by my hand. Now let's take a closer look. On the oscilloscope, we have the receiver's signal, which is inputted by the user. Currently, the wheel is at rest. As we rotate to make a hard right, we can see that the pulse increases in width. At maximum width indicates a hard right turn. The minimum width indicates a hard left turn. You can also see that there is a delay before the control surface reaches the far right or far left position, despite the user already inputting to do so. After probing around, I found the pin which indicates the current position of the control surface. I soldered an orange wire so I could connect it to the oscilloscope. The position of the control surface is determined by the wiper on the potentiometer, which acts as a voltage divider. Maximum voltage indicates a hard right turn, while a minimum voltage equals a hard left turn. The yellow line on the oscilloscope displays the voltage of the potentiometer. When the voltage is high, it indicates the control surface is currently in the far right position. When the voltage is low, it indicates that the control surface is currently in the far left position. The green pulse is the same pulse as before, the user specified position. As I turn the wheel back and forth, we can see the pulse change, which indicates the change in the sent signal, and a change in the pot's voltage, which indicates a change in the current position of the control surface. As you can see, there is a delay before the control surface reaches the value specified by the user. I soldered 2 yellow wires to each end of the DC motor so that I could connect them to the oscilloscope. On the oscilloscope, we can see the current motion of the motor. Currently, a resting position signal is being sent by the user on the receiver. When I force the control surface to a different location, we can see that the motor reacts so that it can return to the home position, as the pot knows that it is not currently in the correct position and tells that microcontroller, which then responds by moving the motor so that it can adjust for this and go to the correct position specified by the user. Here we have a basic dynamic schematic of the motor. On the left, we have the torque of the motor, and omega is the rotational speed of the motor. On the right, we have the load of the control surface, which would vary depending on where the servo motor was installed. Here we have the basic torque equation of the DC motor. Tm is the motor's torque, TL is the torque of the load caused by the control surface, J is our polar moment of inertia, and omega m is the angular velocity of the motor. We can simplify this equation by assuming that our polar moment of inertia does not change over time. By assuming this, we can find that the torque of the motor is determined by the torque of the load plus the polar moment of inertia times the change in the angular velocity of the motor. The bottom equation indicates the components of the torque of a DC motor, in which phi is the flux per pole, p is the number of poles, z is the number of conductors, I is the current, and a is the number of parallel paths. Here is a summary slide discussing the various things that we went over in this video.